Hello everyone, welcome back to another lecture on complex analysis, and today it is fourth lecture on this series which is addressed for undergraduate students. So the very first thing that we have discussed is the complex variable which is represented by Z. These symbols are very important and repeatedly we'll have to use this, that's why I am writing this there. And once you have Z there, we have the function of the complex variable represented by W. And the W can be decomposed into the real and imaginary parts. That's why you write down as U plus IV. So the symbols U, symbols V, symbols W will take their own meaning, okay, unless otherwise specified. So if nothing is specified, you yourself understand that W means function of the complex variable, and it means that it is mapping or transformation. So these things are implied unless something else is stated. And that's one thing. And the next thing that we have completed our discussion is on the equation of the circle that looks like this. So you should always remember that. And in particular, in yesterday's class, we have seen the equation of the directed line, which is looking either like 4 or like 5. Both of them are equation of directed line. 5 is nothing but the parametric representation of equation 4. Okay, 4 and 5 are same. Okay. 5 is the parametric representation and 4 is the generic representation. And here you should always remember which is real, which is complex. Those things we have already done in the last class, so no need to repeat. But just for information, I will tell that A is a complex number, B is a complex number excluding 0, and T is a real parameter. So these points are very important. Simply writing down this particular equation, you may not do it correctly when you are doing this, solving the problems. Okay. So when you are attempting to solve the problems, you need to know which is real, which is complex. So that is why I am emphasizing these points. Okay, fine. And what is that you want to do today? So today we are going to take an example. We can always solve problems based on whatever concept that we have. Suppose if you have a question like this, of course this is a typical question that you can always observe in GATE examination. The objective of the question is to find the upper bound of the function of the complex variable given by something. So as you can see that some Z is appearing there, which means certainly this is a function of Z. So this function of Z is called the function of complex variable. The question is to find the upper bound. Upper bound means the limit at the top, and that's called the maximum value, right? So if you don't, this is the mathematically technical word is upper bound, but if you just want to know what it is, it's actually a maximum value. So find the maximum possible value for this particular function, subject to the condition. Of course, there's a condition is there. If the condition is not given, you can't find the maximum value. So there's a condition is there. If subject to the condition that modulus of Z equal to 2. So if the condition changes, then the maximum value will also change. So the question should be clear that we are interested to find the maximum. You can also ask another question, find out the minimum value of this. Fine. You can like this, you can keep changing the questions. But we cannot directly jump into the solution to this problem unless we know some quantity on modulus. Okay, you see that there is a modulus here. This kind of modulus we need. So we need to know how to do some calculations with the absolute value or the modulus of a complex number. Only then we can come back here and then see what is the answer. So today's objective is to learn how to play with the modulus of complex numbers. That's an idea. And once things are clear, we'll come back to this solution. So let me therefore come here and then write down what is that we would like to know. So now that we have Z equal to x plus iy, suppose Z is x plus iy, then naturally Z bar, or we say Z bar, either we can write the bar version or star version. So we say that Z star is equal to x minus iy. If this is the situation, this clearly tells you that you can always multiply these two quantities, Z into Z star, and then let us simplify this. This becomes x square, then I square, then you have y square, and that gives you x square plus y square. So this is what you have it on one side of the calculation. Okay. So finally our conclusion is Z into Z bar is given by this quantity. So this is one calculation that goes separately, independently. Now we have another calculation that we will do here. This is what we are going to do is by definition, the absolute value of a complex number. Okay, this is by definition. Let me therefore write down here DEF. Here, and I am writing DEF here, you understand that it is by definition. So this kind of statement is not necessary if you write DEF here. So this is by definition. You have this expression square root of x square plus y square. Okay, so this is basically coming from coordinate geometry. Diagonal like this, then what is the value of the hypotenuse? So certainly this distance will be equal to square root of x square plus y square. That is what is coming here. So therefore this calculation stays independent of this calculation. So don't think that these two things are coming similar, but that's coming similar, that's different, but they are not coming from here. So this is staying independently and this calculation is independent. Now what you do is you compare this one with that one. Okay, so by comparison of this, so what we get is, so you just want to compare this with the modulus of z. What we have is this quantity z into z star, or we say z into z bar, nothing but mod z. Okay, because this square root we are removing, so for that I have to square here, then that is nothing but this particular quantity, and that is what you are going to get. So this is looking simple equation, of course. Of course, you should say one thing you have to think. It's not a great derivation in the complex analysis, but this is very fundamentally important. We are going to play with this modulus based on this equation. And then we will have to be careful where the square is present. That's what I am going to do here. Okay. So now that we have this relation modulus of z square is equal to the product of the original complex variable with its complex conjugate. Now, once again I will repeat this. This is not a equation to be remembered like mod z square. You have to remember like a black box equation. Okay, so you don't remember that mod z square is z into z bar. Okay, there's no much use of that. How you have to remember this? There is some complex variable. I don't know what it is. Okay, so something is there, something like alpha plus I beta, whatever it is, some complex variable is there here, and then I would like to do this modulus of square. So this is your complex variable. I'll write like this CPX VAR to say that some complex variable is there here, and then I'm going to take this modulus. How do you understand this? The original complex variable I'll write like this, multiplied by the complex conjugate of that. Okay, so you see this is a complex variable that you have. This is complex conjugate of that. This product is like this, you have to remember, not just z here. Okay, you cannot expect every time z only, anything else can be there in place of that. So that's why this quantity inside the bracket is what is called a black box. Okay, so some box is there here, I don't know what is there inside that. I want to do this mod square is nothing but that multiplied by this square. So like this you have to understand, and inside the black box you can put any complex variable you like. That's what you have to remember, not just z alone. That is the meaning implied by this equation. So you have to be careful. Now when we do some calculation, you can understand that. Fine. How can you write 1 over z? So 1 over z can be written like this. 1 over z into, you multiply and divide by complex conjugate, and then that gives me z bar divided by mod z square. So now and then we have to do this replacement. So whenever you see an 1 over z here, you replace it by z bar divided by mod z square. So that is another important relation which is required. So let me write down that this is 2. So whatever is a relation that you have to give some importance, I am putting a box there. It is not like what you do in school, you keep box and keep remembering all the formulas. I am not asking you to remember or memorize the formulas, but rather these are the results that we obtained starting from very elementary consideration. You see how we are deriving all these things just by taking x plus iy, only 1, that's it. This is complex conjugate of the original. So start from here, you can derive whatever you want. So it is not that I am asking you to memorize them. Okay, at any point of time you must be able to get this in a matter of 5 minutes. Okay, so even in examination, if you forget some equations, don't worry, you take some rough paper and then quickly do it. That's the idea. Now apply equation 1 to z1 and z2. Now what you want to do now? Now we are going to obtain another relation. So if you are going to write like this, for the variable z1, I can write like this. So that is where z1 into z1 bar, and similarly you can write down z2 into z2 bar, and this is b. So now we'll multiply this a and b now. So then we get modulus of z2 square would be equal to, multiply this into these two things will give you z1 bar, z2. So which can be simplified like this, z1 z2 multiplied by z1 z2 whole bar. So this is equal to this, isn't it? So therefore, based on this, what happens is, this is what is I am calling black box. If this is a black box, then this is the complex conjugate of the black box. So what do you understand by that? By that we mean to say that this is z1 z2, then you have a whole square. So black box into conjugate of black box is nothing but square of the modulus of the black box. Like that you have to remember. Okay. So once this is clear, the manipulation is clear, then you copy this left hand side here, then I will be getting modulus of z1 square, z2 square is that, and take the square root on both sides. If I take square root on both sides, I can get and that must be equation number, I think 3. We have like this. Okay, so this equation is very important. Things are, many of the things look too elementary or too simple. Okay, whatever you feel, it may be too simple, but this is where we are going to, most probably people will make mistakes, especially in the competitive examination. So why this is important, I will tell you what is the importance here is that there is something called a distributive property. So the modulus, you have this modulus, right? Modulus is distributed. You see that this modulus is for a single object. Here the modulus is coming for two objects. That means modulus is for first fellow also. Modulus is used for the second fellow also. That means modulus is distributed to everybody. If there are 4 complex number here, to all the 4 people the modulus will be distributed. Therefore we say that modulus function, complex modulus, is distributive provided multiplication is there. It's very important concept. Why it is very important is, if you are going to do it for addition here, now it is multiplication. If you are going to do it for addition, you will discover that it is not distributive. So the distributive property fails for addition and subtraction, whereas distributive property is true for the case of multiplication and division. Okay, so this is multiplication. For division, straight away you write down z1 divided by z2. You write down here, then you say that modulus of z1 divided by modulus of z2. And all the other story will be valid. Only thing is that it is applicable for multiplication also, division also. But for plus and addition it is not valid. That is the place where mistakes will happen. So this is where 3. Okay, so now we will go to the next expression where we can go for addition and subtraction. Fine. Prepili? Okay, now that we have this product rule, okay, there's a product here, that's what I mean to say. Of course, the product is there here also, you are actually multiplying here. So the product of the two complex numbers we can have, and then the complex modulus is distributive. So we are naturally asking the question, what happens if there is a plus here? That means, so now what you understand is, this dot is replaced by plus, dot is replaced by plus. So this is true, this is wrong. So therefore, this is what you have to understand. This is what I am trying to say. So this expression is invalid, which means that if you want to make it correct, then this is not equal. That's what I mean to say. If it is not equal, then naturally the question comes, what is that? So you need to know some information, and that's what we are going to work out. Okay, Z1 is nothing but, so this much distance x and that much distance y, and that's the Z1. Similarly, Z2 is another complex point. So I have drawn one complex point here, the another one is there. Now these lines are going to represent this. So that's why I have drawn this particular line here. So this is a distance from the origin to the point. This is the distance from the origin to the point. That's fine. Okay, so you have to be clear. You have to be clear about which is complex number. This is complex number. If I put that, it is not a complex number. Please understand that once I put the complex modulus, it becomes a real number, isn't it? So, which is complex number? Z1 plus Z2 is complex number. Whereas, once I put the modulus, it becomes a real number, no longer complex. Okay, so therefore, you ask the question, where is Z1 plus Z2? It is here. This is, let us say that this is my Z1 plus Z. You have to understand how it is so. It's quite very easy to understand. From here to here is x value, for this x value. What should I add here? I have to add the real part of x2. So x2 has this much amount of real part. So if I come here, this is the real part. So this real part plus this real part, if I add everything, where it will go? It will go away from this, no? That is there here. So that's how that point has come. Okay, so the idea is that this Z1 plus Z2 will represent the diagonal of the parallelogram, and the parallelogram itself, you have to understand that it is obtained by completing all the sides from Z1 and Z2. That's all about it. And of course, the only confusion that sometimes people will get is that how this line you can draw here, because Z2 is from here to here only. Okay, that is only sometimes some students get a doubt. Where from you got a line here? There is no line originally. Originally, you have this line for Z2 and that line for Z1. Only two lines are there. So how you got this line is nothing but this one you simply copy paste here. Okay, so I have this length here. Suppose if this is 1 meter distance, same 1 meter distance I put a stick here. That's all about it. It is simply a translated version of this original Z2 here. Okay, only to make this particular parallelogram I am making. So therefore, at the same time there is very important thing. This line does not represent Z2, because that is a careful thing you have to be there. Sometimes people will get confused. Is this Z2? No. Is this Z2? Yes. So then what is this actually? This is nothing but a translated version of the Z2, but still this length is preserved. So this length is equal to this length. Therefore geometry is not spoiled. So as far as length is concerned, you can move it. But if you want to consider complex number as such, you cannot move it. Because once you move the complex number, all numbers are changing. Okay. Whereas by moving, nothing happens to the length. And similarly, what happens is, this is my Z1 and that is the length of Z1. I can also take a copy of this length and keep it here. So that is that line. So I am keeping a copy of this line there just to make it equal values and then make a parallelogram. So once you do that, then once your construction is over, I don't want this line. Technically, this line is not required because this is only for construction. So once you understand the construction is over, I have discovered the point there. Once I discovered the point, this line and that line are not at all required. Now it is clear that this is Z1, that is Z2, and this is Z1 plus Z2. So that's all. This is only for construction purpose. But sometimes people get confused that this is actually Z2. It cannot be. Okay. So with that idea, okay, so everything is clear now. Now what do you want to conclude? So the conclusion is very important because we have asked the question, what is the value of this modulus? And this is mod Z1. Mod Z1 represent length. Z1 represent complex number. That means point itself. This is the point. Length means from here to here. So from here to here is mod Z1. This point is Z1. This length is nothing but this length because it is the same thing copy pasted. Now you tell me what is this length? This length is Z2. If this is Z2, then this length is mod of Z2. So if this is modulus of Z2, then that is also modulus of Z2. Is this point clear? So this distance is modulus of Z1, that distance is modulus of Z2. Then what is this distance? It is modulus of that. Therefore, this is nothing but modulus of Z1 plus Z2. And now you forget about the parallelogram. We don't want parallelogram. Now you see a triangle. There is a triangle from here to here, and there to there. So once you have a triangle, so you tell me which is the longest side. The diagonal is the longest one, longer one. Fine. These two things are small fellows, I agree. But suppose if you add them separately, if this is 3 and this is 7, 3 plus 7 is 10. Will it be 10? No. That means the length of the diagonal is going to be less than the sum of the two sides. This is quite directly visible from the triangle. Therefore, immediately you write down this result that modulus of Z1 plus Z2 is less than or equal to, in particular I will write down less than, okay, it's less than modulus of Z1 plus modulus of Z2. Okay, so that is the result that you have. You see that this is coming only from the diagram. That's why the diagram I am explaining time. We are not doing any mathematical derivation. There is no lengthy mathematical derivation. But you can see that what is the conclusion is modulus of Z1 plus Z2. This means that mod Z plus mod is not equal to, unless there is a special situation where it is equal. When it will be a special situation is that like this, everything should be parallel. Z1 is this, Z2 is this. If everything is parallel to each other, then it will become equal. Okay, that means you no longer have any triangle. If everything is a straight line, if this is Z1 and that is Z2, same continuation of the same line. If it is continuation of the same line, then the summation will be equal to same. Okay, so this is not in general true. Okay, so it is not in general true. Okay, only in parallel case it will be equal. So let us not worry about the parallel case. And therefore, because of this reason, this is what you have to remember. So let me therefore make a final conclusion that in all the cases it will be less than only. Only in special case of parallel Z1 and Z2, equality is valid. Okay, in all other cases equality is not valid. It is always less than. So that's the point you remember. So in general, what you will do is both will happen this or that, and therefore we will write like this. Then make a conclusion that this is the one. So let us say that this is your equation number 4. Right. So now this relation is very important. This is also known as the triangle inequality. Inequality means less than is less than, greater than. Whenever less than and greater than is coming, then it is known as inequality. So this is known as the triangle inequality because the relation is taken from triangle. Now using this, what happens is you can generate some more relations. Okay, and why these kind of relations are important? Now you tell why it is important, because we started with an example problem. The example problem is, what is the question is, find out the upper limit or upper bound. Upper bound means what? Maximum value. Now you see what is this, less than or equal to. Now you have to tell this is important actually. Why it is important, you see. Less than or equal to something. The meaning is that the something that you have a number, right, that number is a maximum value. Do you agree? Means whatever you write here, something is maximum value. That's the meaning. Less than or equal to means that's the highest value. Any number you tell, it will be below that. So therefore, this maximum value, this whatever I am going to tell, this is called upper bound. Upper bound means what is the upper limit? You can't go above that. So find the upper bound means find the maximum value. Find the maximum value means you write down the equation given by less than or equal to something. That's all. You do whatever you like. So do whatever algebra you like, you manipulate whatever way you like, but you bring the equation such that less than or equal to something, then that something is the maximum value and is the upper bound. So that's an idea of this particular example problem. So I told you that we will do the problem, but before jumping into that problem, I want to derive one more relation similar to this. Okay, after that only we will be comfortable to move that. So therefore I will derive the equation number 5. Right now 4 is there. Let us complete the equation number 5 and then go to the solution to the problem that we will do in the next class. So stay tuned and then write down some comments, whatever question you want. Are you following this or not? Okay, if there is any difficulty, whatever is there, you write down in the comment section. So we'll see that in the next class. Okay, thank you.